Welcome to Earthly Teachings, where learning is clear and powerful. Today, we are working on Mathematics N6, and we'll be diving deep into solving linear first-order differential equations. Let's learn together. In this video, you will learn how to identify, set up, and solve this specific type of differential equation using a powerful method called the integrating factor method. By the end of this tutorial, you will be able to first, define what a differential equation is and differentiate between linear and nonlinear types. Second, solve linear first-order equations by calculating an integrating factor and applying a standard formula. And third, you'll learn how to find specific solutions, known as particular solutions, using initial conditions. This method is a core skill in N6 maths, so let's get started. Our first step is to recall some fundamental concepts about differential equations. This is revision from N5 mathematics. So what is a differential equation? It's an equation that contains a function and its derivative or derivatives. The simplest way to think about it is an equation that connects the rate of change of something to the quantity itself. The order of a differential equation is determined by the highest derivative present in the equation. For example, in the equation dx plus y equals x, the highest derivative is dx. This is a first-order derivative, so the equation is a first-order differential equation. In d squared e over dx squared plus dx equals 0, the highest derivative is d squared e over dx squared, a second-order derivative. Therefore, this is a second-order differential equation. In this video, we will focus exclusively on first-order equations. Now let's talk about the degree of a differential equation. The degree is the power, or the exponent, of the highest-order derivative. Let's look at the example dx squared equals x. The highest derivative is dx, and it is raised to the power of 2. So, the degree of this differential equation is 2. Today's learning objective, recalling these definitions, has been achieved. We have successfully revised the concepts of order and degree for differential equations. Our next objective is to distinguish between linear and nonlinear differential equations, which is crucial for determining the correct solution method. We must learn the difference between linear and nonlinear equations. A linear differential equation is one that follows a specific strict structure. There are 3 key rules for an equation to be considered linear. Let's write them down. First, the dependent variable, usually y, and all its derivatives, like dix, must have a power of 1. You cannot have them squared, cubed, or raised to any other power. Second, there can be no product of the dependent variable y and any of its derivatives. In other words, you will never see a term like y times dx. Third, the coefficients of y and its derivatives can only be constants or functions of the independent variable, x. They cannot be functions of y itself. Now, let's look at some nonlinear examples to solidify our understanding. First, consider dx squared plus 4y equals 3x. This is not linear. The reason is the degree of the derivative dx is 2, not 1. This violates our first rule. Next, let's examine d squared e over dx squared plus 4y squared equals 3x. This is also nonlinear. Why? Because the power of the dependent variable y is 2, which is more than 1. This breaks the first rule again. Finally, look at y times dx plus sin x equals tan x. This is nonlinear because it contains a product of the dependent variable y and its derivative dx. This violates our second rule. You now have a clear understanding of the difference between linear and nonlinear equations. We can move on. Having defined differential equations, we can now state our main goal for today's video. Our objective is to solve a very specific type of equation, a linear first-order differential equation. In N5, you might have encountered the method of separation of variables. Let's briefly recall what that was. Separation of variables involves rearranging the equation so that all terms involving y and di are on one side, and all terms involving x and dx are on the other side. Once separated, you can integrate both sides. This method is elegant, but it only works if you can successfully separate the variables. Unfortunately, many linear first-order equations cannot be solved using separation of variables. This means we need a more general and powerful method. That's why we're learning the integrating factor method. This method allows us to transform a non-separable linear equation into one that is integrable. It's a key tool for your N6 toolkit. Let's begin by defining the standard form of a linear first-order differential equation. This is the template we will always use to start. The standard form is dx plus p times y equals qx. It is crucial to remember this form. The left side must have the derivative dx with a coefficient of +1 and the pi term. The right side is a function of x, qx. Let's identify the parts. Px is the function of x that is the coefficient of y. Qx is the function of x on the right side. Notice that the p in px and q in qx will correspond to what you see in the problem. An important side note, you might also encounter equations where x is the dependent variable and y is the independent variable. In this case, the standard form changes to dx di plus p e py times x equals qy. Everything is flipped. We'll see an example of this later on. For now, we'll focus on the more common form, with I as the dependent variable. So remember your first task when given any linear first-order differential equation. Rearrange it into the standard form di dx plus px equals qix, and correctly identify p by dx and q by x. This is the foundation of the entire process. Now, let's introduce the tool that will do all the work for us, the integrating factor. Our objective is to learn the formula for the integrating factor and how to derive it. The integrating factor is a special function that, when multiplied throughout our differential equation, transforms the left side into something we can easily integrate. The integrating factor, abbreviated as IF, is given by the formula e to the power of the integral of p x dx. Remember, the EE is Euler's number, a constant approximately equal to 2.718. It's a powerful tool, and let's see why by deriving the general solution formula. We start with our standard form, di as dx plus pi x q. Note that I'm using p and q as shorthand for px and qx. Now, let's multiply every single term in the equation by our integrating factor, e to the integral of pd. This is the magical step. Let's focus on the left side. E to the integral of p dx times diet dx plus p times y times e to the integral of p dx. This looks complicated, but it's not. It's the result of applying the product rule for differentiation. Specifically, the left-hand side is the exact derivative of the product y times e to the integral of p dx. We can write this as dot dx of the quantity y times e to the integral of p dx. Let's quickly verify this. Using the product rule, the derivative of u times v is u prime v plus v prime u. If we let u be y and v be our integrating factor, e to the integral of p dx, then u prime is di slash dx. What is v prime? The derivative of e to the integral of p dx is e to the integral of p dx times the derivative of the exponent. The derivative of the integral of p is just p. So v prime is p times e to the integral of p dx. Plugging these back into the product rule, u prime va plus v prime u, we get dx times e to the integral of p dx plus p times e to the integral of p dx times y. This is exactly the left-hand side of our multiplied equation. The integration factor method works because it's designed to reverse the product rule. So, we can rewrite our equation as the derivative of the product on the left and q times the integrating factor on the right. Now for the final step, integration. To get y by itself, we need to get rid of that derivative on the left-hand side. We do this by integrating both sides with respect to x. The integral of a derivative simply cancels out the derivative, leaving us with y times e to the integral of p dx. On the right, we have the integral of q times e to the integral of p dx. plus an arbitrary constant of integration, c. And there you have it. This is the general solution formula for any linear first-order differential equation. You'll typically find this in a list of formulae for your exams. We have now derived the integrating factor method and its general solution. Let's summarize the procedure into a step-by-step guide you can follow to solve any problem of this type. I recommend you write these steps down as they are your roadmap to success. Step 1. Rewrite the given equation in the standard form. di dx plus p of x times y equals q of x. This is your starting point. If the equation isn't in this form, you must manipulate it algebraically until it is. Once it's in standard form, identify what p of x and q of x are. Step 2. Determine the integrating factor, if, using the formula e to the integral of p of x dk. Integrate p of x and then raise e to that power. Step 3. Calculate the integral of q of x times the integrating factor. This is often the most challenging part, as it might involve various integration techniques like integration by parts or substitution. Step 4. Use the general solution formula. Y times the integrating factor equals your result from step 3 plus the constant of integration. This gives you the general solution, which contains an arbitrary constant c. Step 5. If the problem provides initial conditions, a specific value for y when x is a specific value, substitute these values into your general solution to solve for c. This will give you a particular solution, which is a single, unique function that satisfies both the differential equation and the initial conditions. By following these 5 steps systematically, you will be able to solve any linear first-order differential equation. Let's move on to some examples. Before we tackle a full problem, there's a very common simplification we'll use frequently. This objective is to master simplifying exponential and natural logarithm expressions. We very often need to simplify expressions like e to the power of the natural logarithm of some function. The key property to remember is that the exponential function e to the x and the natural logarithm ln x are inverses of each other. Because they are inverses, they cancel each other out. So, e to the power of the natural logarithm of any expression is simply that expression itself. For example, e to the power of ln of 5 is simply 5, or e to the power of ln of secant x is simply secant x. Often, the expression will require a small manipulation first. We will use the power rule for logarithms. M times ln of x equals ln of x to the mth power. For example, consider e to the power of 2 ln of sin x. We can't cancel e and ln directly because of the 2. First, use the power rule to move the 2 inside the logarithm. It becomes e to the power of ln of sin x squared. Now, e and ln cancel, and we are left with sin squared x. Let's try one more. The note provides several examples, but let's do another to reinforce the process. Consider e to the power of ln of x minus ln of secant x. Using the division rule for logarithms, ln x minus ln y equals ln of x divided by y. This simplifies to e to the power of ln of x over secant x. The e and ln cancel, leaving us with x over secant x, which we know is equal to x times cosine x. See how these rules make complex expressions manageable? Mastering these exponential and logarithmic identities will make calculating your integrating factors much quicker. We have successfully practiced simplifying these expressions. Okay, it's time for our first full worked example. We will determine the general solution of the equation, x squared plus 1 times dx plus 2xi equals x secant squared x plus tangent x. Step 1, standard form. The first thing we need to do is rearrange this into our standard form. Remember, the standard form requires the coefficient of dx to be 1. Right now, it's x squared plus 1. So we must divide every term in the equation by x squared plus 1. Doing that gives us dx plus 2x over x squared plus 1 times y equals x secant squared x plus tangent x, all over x squared plus 1. Now we can identify p of t and x. Px is the term multiplying y, which is 2x over x squared plus 1, and qx is everything on the right side. Step 2. Integrating factor. Now we calculate the integrating factor. If equals e to the integral of p e d dx. We need to integrate 2x over x squared plus 1. This is a standard integral form, f prime over f, whose integral is ln of the absolute value of f k. Here the derivative of the denominator, 2x, is exactly the numerator. So the integral is ln of the absolute value of x squared plus 1. Since x squared plus 1 is always positive, we can drop the absolute value. This gives us e to the power of ln of x squared plus 1, which simplifies to just x squared plus 1. Our integrating factor is x squared plus 1. Step 3. Integrate qx times the integrating factor. We need to calculate the integral of q times if. Let's substitute our expressions. Q is the fraction we found, and if is x squared plus 1. Notice what happens. The x squared plus 1 in the denominator of q cancels with the integrating factor. This leaves us with a much simpler integral, the integral of x secant squared x plus tangent x. We can split this into two separate integrals, the integral of x secant squared x and the integral of tangent x. Let's work on the first one, the integral of x secant squared x. This requires integration by parts. We use the rule u dv e uv v du. We'll set u equal to x because its derivative is simpler. So dv is secant squared x dx. Then du is dx, and the integral of dv is v equals tangent x. Applying the formula, we get x tangent x minus the integral of tangent x dx. See that? The integral of tangent x has just appeared, which is convenient. Now, let's substitute this back into our main calculation. We have x tangent x minus the integral of tangent x dx plus the integral of tangent x dx. The two tangent integrals cancel each other out. This leaves us with just x tangent x. So, step 3 simplifies beautifully. Step 4, general solution. We now assemble our final answer using the formula. The formula is y times if equals the result of step 3 plus c. Plugging in our values, we get y times x squared plus 1 equals x tangent x plus c. This is the general solution. It includes the arbitrary constant c, which means it represents an infinite family of curves. We have successfully found the general solution for example 4.1. Here's our second example. We need to find the general solution of dx minus y times tangent x plus cotangent x equals cotangent x. This problem has a special trap, so pay close attention to the details. Step 1. Standard form. The equation is already in standard form, but there's a crucial point. The note in the text says, take p and q together with the sign. This is vital. Our formula is dx plus y. In our equation, we have a minus. Therefore, p as x is not tan x plus cot x, but negative tan x plus cot x. Qx is cot x. Let's repeat that to be perfectly clear. Our px is negative. Px equals minus tangent x plus cotangent x. This is the #1 mistake students make on problems like this. Qx equals cotangent x. Step 2. Integrating factor. Now we calculate the integrating factor. If equals e to the integral of p exd. So we need to integrate negative tan x plus cot x. The text shows two methods for this integration. Let's use the first method, which simplifies the expression before integrating. The integral is negative of the integral of tangent x plus cotangent x. We know the integrals of these basic trig functions. The integral of tangent x is ln of secant x, and the integral of cotangent x is ln of sine x. Using the logarithm property that the sum of logs is the log of a product, we get negative ln of the absolute value of secant x times sine x. Secant x is 1 over cosine x, so secant x times sine x is tangent x. The expression becomes negative ln of tangent. Now use the power rule for logarithms. Minus ln of tangent x is the same as ln of tangent x to the power of minus 1, which is ln of 1 over tangent x. And we know 1 over tangent x is cotangent x. This gives us e to the power of ln of cotangent x. The e and ln cancel, and our integrating factor is simply cotangent x. Step 3. Integrate qx times the integrating factor. We need the integral of q times if, which is the integral of cot x times cot x, or the integral of cot squared x. To integrate cotangent squared x, we use the trigonometric identity. Cotangent squared x equals cosecant squared x minus 1. The integrals of these are straightforward. The integral of cosecant squared x is negative cotangent x, and the integral of 1 is x. Step 4. General solution. Our general solution formula is y times if equals the integral we just found, plus c. Substituting in our if and the integrated expression, we get y cotangent x equals negative cotangent x minus x plus c. And that is our general solution for example 4.2. Notice how critical it was to correctly identify the sign of pt. Welcome to example 4.3. In this one, we'll encounter another common integration technique. We need to find the general solution of di dx plus 2xi, 1 plus 2, equals tangent inverse of x, 1 plus 2. Step 1. Standard form. The equation is already in standard form, di x plus pxy equals qx. We can immediately identify ptk and qx. Px is 2x divided by 1 plus x squared. Qx is tangent inverse of x divided by 1 plus x squared. Step 2. Integrating factor. Let's calculate the integrating factor. If equals e to the integral of p equals dx. This is the integral of 2x over 1 plus x squared, which is the f prime over f form again. The integral is ln of the absolute value of 1 plus x squared. Since 1 plus x squared is always positive, the absolute value is not needed. The e and ln cancel, leaving us with our integrating factor, 1 plus x squared. Step 3. Integrate qx times the integrating factor. We need to find the integral of q times if. Notice that the denominator of q, which is 1 plus x squared, cancels out perfectly with our integrating factor. This is a very common and intentional outcome of this method. We are left with a single integral to solve, the integral of tangent inverse of x. This integral requires integration by parts. Let's set it up. When integrating an inverse trigonometric function, it's a good strategy to set that function as u and dv as 1. Applying the integration by parts formula, uv minus the integral of v du, we get x times tangent inverse x minus the integral of x over 1 plus x squared dx. The remaining integral is again of the f prime over f type. The derivative of 1 plus x squared is 2x. We have x. So we'll multiply the top and bottom of the integral by 2 and compensate with a 1/2 out front. This gives us x tangent inverse x minus 1/2 times the integral of 2x over 1 plus x squared dx. Now we can solve this. The integral is ln of the absolute value of 1 plus x squared. Adding our constant c, we get our final expression for step 3, x tan 1x, 1 plus x2 plus c. Step 4. General solution. The formula is y times if equals our result from step 3. Substituting everything in, we have y times 1 plus x squared equals x tangent inverse x minus 1/2 ln of 1 plus x squared plus c. And this is the general solution for example 4.3. This problem was an excellent demonstration of using integration by parts, another tool you need to be comfortable with in N6. Our next example, example 4.4, will look a bit different at first glance, but we'll see that it fits our model perfectly once we rearrange it. We are asked to find the general solution of di minus y dx equals x dx. Step 1. Standard form. First, let's get rid of the differentials dx and di in this format. We do this by dividing the entire equation by dx. Dividing every term by dx, we get di dx minus y dx over dx, which is just y, equals x dx over dx, which is equal. So the equation becomes di dx minus y equals x. This is the standard form we know. Remember the sign convention we discussed earlier. Px is the coefficient of y. Since we have minus y, px must be negative 1, and qx is x. Step 2. Integrating factor. Now we calculate the integrating factor. If equals e to the integral of p dx, here p piece is a constant negative 1. The integral of 1 is simply x. So our integrating factor is e to the power of negative x. Step 3. Integrate qx times the integrating factor. We need the integral of q times if, which is the integral of x times e to the power of negative x. This integral requires integration by parts. Let u equal x, so do is dx. Let dv equal e to the negative x dx, so v is e to the negative x divided by what 1, or negative e to the negative x. Applying the formula uv minus v du, we get x times negative e to the negative x, minus the integral of negative e to the negative x dx. The two negative signs in the second term cancel. This gives us negative xe to the negative x, plus the integral of e to the negative x dxe. The integral of e to the negative x is again negative e to the negative x. So our expression for step 3 is negative xe to the negative x minus e to the negative x plus c. Step 4, general solution. Our general solution is y times if equals the result of step 3. Substituting, we get y times e to the negative x equals negative xe to the negative x minus e to the negative x plus c. The solution manual simplifies the right side by factoring out e to the x. Let's do that to match. Factoring out e to the x from the first two terms gives gish e to the x times x plus 1. So the final general solution is ye to the negative x equals negative e to the negative x times the quantity x plus 1 plus c. This example showed us that even if a differential equation doesn't look like our standard form at first, we can often rearrange it into the correct format. We also got more practice with integration by parts, which is a key skill for solving these equations. Example 4.5 is another great one for practicing integration by parts, but with a clever twist. The question asks for the general solution of dx minus yx equals e to the x times the quantity 1 minus 1x. Step 1, standard form. The equation is already in standard form. Identifying px and qx is straightforward. Px is the coefficient of y, which is 1x. Remember to get the negative sign. Qx is everything on the right-hand side, e to the x times 1 to 1x. Step 2, integrating factor. Let's find the integrating factor. If equals e to the integral of itx dt. The integral of what is that lex. Using our power rule for logarithms, becomes e of x to the u1, or in of 1 e. The e and ln cancel, and we get an integrating factor of 1 e dx. Step 3, integrate qx times the integrating factor. We need the integral of q times if. We multiply our q term by 1 x. Let's expand the expression inside the integral. Multiplying through by 1 cos, we get the integral of e to the x over x minus e to the x over x squared. Let's write this as two separate integrals. Now, here's the trick. The text says to use integration by parts for the first integral only. We'll apply integration by parts to the integral of e to the x over x. Let u be 1 t, so do is y x squared dt. Let dv be e to the x dx, so v is e to the x. Plugging into uv minus v du, we get 1 e by x times e to the x, minus the integral of e to the x times x squared dx. The two negative signs cancel, giving us e to the x over x plus the integral of e to the x over x squared dx. Now let's substitute this result back into our main calculation for step 3. We have the result of the first integral, e to the x over x plus the integral of e to the x over x squared, minus the second original integral, the integral of e to the x over x squared. What happens? They cancel out. This is a classic technique. The integration by parts of the first term generated the negative of the second term, simplifying the entire expression to just e to the x over x, plus our constant c. Step 4, general solution. Putting it all together, y times our integrating factor of 1 by Hans equals the result we just found, e to the x over x plus c. This is our general solution. This example was a great exercise in recognizing and exploiting cancellations after integration by parts. Our next example, example 4.6, will involve a trigonometric integral that can be solved using a simple substitution. We are asked to find the general solution of dx minus y sine x equals sine x. Step 1. Standard form. The equation is already in standard form. Carefully identify p tied to x and q x. Pex is the coefficient of y, which is negative sine x. Qx is the term on the right, which is sine x. Notice again that the negative sign from the y term is part of pi taz. Step 2. Integrating factor. Let's calculate the integrating factor. If equals e to the integral of p x dx, which is e to the integral of negative sine x dx. The integral of negative sine x is positive cosine x. Now, can we simplify this? No. The e to the ln x ex rule only applies when the exponent is the natural logarithm of something. Here it's just cosine x. So the integrating factor is simply e to the power of cosine x. This is a common point of confusion, so be careful. Step 3. Integrate qx times the integrating factor. We need the integral of q times if, which is the integral of sin x times e to the power of cosine xd. To solve this, we will use a u substitution. Look for a function and its derivative. Let's choose u to be cosine x. The derivative, do dx, is negative sine x. Rearranging for dx, we find that dx is equal to do divided by negative sine x. Now substitute these into our integral. We have the integral of sine x times e to the u, all times do over negative sine x. The sine x terms cancel perfectly. We are left with the integral of negative e to the u do. The integral of e to the u is just e to the u. So we have negative e to the u plus c. Finally, we substitute u back with cosine x to get negative e to the cosine x plus c. Step 4. General solution. Our general solution formula is y times if equals our result from step 3. Substituting the integrating factor e to the cosine x and our integral, we get y times e to the cosine x equals negative e to the cosine x plus c. And there is the general solution for example 4.6. This example was a great reminder that not all integrating factors will simplify further, and that u substitution is a valuable tool for solving the final integral. Example 4.7 is a crucial one because it shows us what to do when our equation is in terms of y, not x. The question is dx plus x equals 1 minus sine y. Notice the sine I term. Our standard form requires p and q to be functions of x. When you see a function of y on the right-hand side, it's a strong hint that you should flip the dependent and independent variables. We'll solve this as an equation in x, where y is the independent variable. Step 1. Standard form, 4x. Our new standard form is dx d plus py equal qi. Let's start with our given equation. To get dx or di by itself, we first subtract x from both sides. This gives y times dx di equals 1 minus sine ai minus x. Now we need the coefficient of dx dt to be 1, so we divide everything by y. This gives dx di equals 1 bar sin y over y minus x over y. Let's move the xy term to the left to match our standard form. Now we have the standard form. We can identify ppy and qy. Py is the coefficient of x, which is 1 over y, and qy is 1 or sin y over y. Step 2. Integrating factor. The formula is similar, but we integrate with respect to y. If equals e to the integral of p pi di. This is the integral of 1 y dt. The integral is ln of y. So our integrating factor is e to the power of ln of y, which simplifies to y. Step 3. Integrate qi times the integrating factor. We need the integral of q times if with respect to y. As before, the y in the integrating factor cancels the denominator in q. This leaves us with the very simple integral of 1 minus sine y di. The integral of 1 is y, and the integral of negative sine y is positive cosine y. So our result for step 3 is y plus cosine e plus c. Step 4. General solution. Our general solution is x times I if equals the result of step 3. Substituting our integrating factor y and our integral, we get xy equals y plus cosine y plus c. This is the general solution for example 4.7. This problem is an excellent reminder to be flexible with your variables. If an equation is nonlinear in y but linear in x, flip it around and solve for x. It's a clever and powerful technique. Now we will move on to finding a particular solution. In example 4.8, we are asked to determine the particular solution of dx plus 2y tangent x equals 2 sine x, given the initial conditions x equals peak e over 4 and y equals 2. Finding a particular solution involves the same steps as finding a general solution, plus one extra step at the end. We'll follow our familiar procedure. Step 1. Standard form. The equation is already in standard form. Pex is the coefficient of y, which is 2 tangent x. Kex is the term on the right, 2 sine x. Step 2. Integrating factor. If equals e to the integral of 2 tangent x dx, we can pull the constant 2 out of the integral. The integral of tangent x is ln of secant x. So we have e to the power of 2 ln of secant x. Now we use the logarithm power rule to move the 2 inside the log. This gives e to the power of ln of secant squared x, which simplifies to secant squared x. Our integrating factor is secant squared x. Step 3. Integrate qx times the integrating factor. We need the integral of 2 sine x times secant squared x to dx. Let's rewrite this in terms of sine and cosine. Secant is 1 over cosine. So we have the integral of 2 sine x over cosine squared x. We can write cosine squared x as cosine x times cosine x. Sine over cosine is tangent, and 1 over cosine is secant. So our integral becomes the integral of 2 tangent x secant x dx. This is a standard integral form. The integral of tangent x secant x is secant x. So the result of step 3 is 2 secant x plus c. Step 4. General solution. Our formula is y times if equals our result. This gives y secant squared x equals 2 secant x plus c. Step 5. Find the particular solution. This is where we use our initial conditions. We are given that when x is pi over 4, y is 2. We substitute these values into our general solution to solve for c. Remember that secant is 1 over cosine. So this becomes 2 divided by cosine squared of pi over 4 equals 2 divided by cosine of pi over 4 plus c. Cos pi 4 is the square root of 2 over 2. Cos squared of pi over 4 is 1/2. This gives us 2 over 1/2 equals 2 over the square root of 2 over 2 plus c. This simplifies to 4 equals 2 times the square root of 2 plus c. Solving for c, we get c equals 4 minus 2 times the square root of 2, which is approximately 1.1172. The final step is to write down the particular solution by substituting this value of c back into the general solution. The particular solution is y secant squared x equals 2 secant x plus 1.112. And there you have it. You've now seen how to find a unique, particular solution by using initial conditions to determine the value of the integration constant. This is a very common type of exam question. Our final example, example 4.9, is another particular solution problem designed to give us more practice with the complete process. We need to find the particular solution of d/r dx plus y cotangent x equals 1 divided by x sine x minus 1, with the initial condition that the curve passes through the point 1, 1, meaning x equals 1 and y equals 1. Step 1. Standard form. The equation is already in our standard form. Pash is cotangent x. Qx is 1 x sine x. 1. Step 2. Integrating factor. If equals e to the integral of cotangent x dx. The integral of cotangent x is ln of sine x. So the integrating factor is e to the ln of sine x, which simplifies to sine x. Step 3. Integrate qx times the integrating factor. We need the integral of q times if. We multiply our q term by sine x. Let's distribute the sine x inside the brackets. The first term becomes sine x over x sine x, which simplifies to 1 over x. The second term is negative sine x. So our integral is of 1 by Pichaz minus sine x. We can integrate these two terms easily. The integral of 1 by Pichaz is ln of x, and the integral of negative sine x is positive cosine x. So step 3 gives us ln x plus cos x plus c. Step 4, general solution. The general solution is y times if equals our integral result. This is y sine x equals ln x plus cos x plus c. Step 5, particular solution. Now we use the initial condition x equals 1 and y equals 1. Substitute x1 and y01 into our general solution. A very important note here, as highlighted in the text, you must be in radian mode on your calculator. This is critical for getting the correct answer. ln of 1 is 0. Sin of 1 radian is approximately 0.8415. Cosine of 1 radian is approximately 0.5403. So our equation becomes 0.8415 equals 0 plus 0.5403 plus c. Solving for c, we find that c is approximately 0.301. Finally, we write the particular solution by replacing c in the general solution with this value. The particular solution is y sine x equals ln x plus cos x plus 0.31. This was a good final example to consolidate all the steps, including the use of initial conditions for finding the particular solution. We've now worked through a variety of examples using the integrating factor method. You've seen how to identify P's and QX, calculate the integrating factor, integrate the Q times IF product, and handle initial conditions. This method is a powerful tool for solving a wide class of differential equations. Today, you have learned to first define differential equations and distinguish between linear and nonlinear types. We established that linear equations have y and its derivatives raised to the power of 1, with no products of y and its derivatives. Second, solve linear first-order equations using the integrating factor method. You can now follow the 5-step procedure. Standardize, find if, integrate q times if. Write the general solution, and if necessary, find the particular solution. Third, determine particular solutions from initial conditions. You know to use the given values of x and y to solve for the constant c. I encourage you to re-watch these examples, paying close attention to the small details and the why behind each step. The key to mastering this is practice, practice, practice. Thank you for watching Earthly Teachings. I hope this tutorial has made this complex topic clear and understandable. If you found this video helpful, please like it, and don't forget to subscribe to the channel for more powerful learning content. Continue learning, and I'll see you in the next video.